Hello viewers, in this chapter we are going to discuss collision. Collision is a short-term event and is said to have occurred if two or more bodies physically collide against each other or the path of one body changes due to the influence of other bodies. It is found that linear momentum before and after the collision remains conserved, and total energy also remains conserved in a collision. In some of the collisions, even kinetic energy before and after collision remains conserved. If the kinetic energy remains conserved, then it is termed as elastic collision, and if kinetic energy does not remain conserved, then it is termed as inelastic collision. If two objects stick together after collision, then this type of collisions are termed as perfectly inelastic collision. Later, we will classify collisions in a more specific manner using the coefficient of restitution. Now, let us focus on elastic collision in one dimension. When two bodies moving along the same straight line collide with each other without loss of kinetic energy and continue to move along the same straight line after collision, it is said to be an elastic collision. Here, let us consider two objects of mass m1 and m2 are moving with velocities u1 and u2 respectively. And after the collision, the velocities changes to v1 and v2 respectively. For a collision to occur, u1 must be greater than u2. At the instant of collision, from the concept of impulse and momentum, we can say that the net external force times the duration of collision should be equal to the change in momentum in the system. If we consider the force of friction and air resistance is negligible here during collision, then there is no net external force acting. Here the only interaction is because of the action-reaction force between the two objects, which means the initial and final momentum in the collision should be the same. Here we can add the individual momentum of the bodies before and after the collision and equate them, which results the following equation: m1u1 plus m2u2 is equal to m1v1 plus m2v2, and we rearrange this equation for more mathematical simplification. Again, we have considered this collision is of elastic in nature. Hence, kinetic energy in this collision should also remain conserved, which can be expressed mathematically as half m1u1 square plus half m2u2 square must be equal to half of m1v1 square plus half of m2v2 square. And again we make some rearrangements. Now if we divide the second equation by the first equation, we obtain a very straightforward relation, that is u1 minus u2 is equal to v2 minus v1. Thus, for a perfectly elastic collision in one dimension, the relative velocity of approach should be equal to the relative velocity of separation. Now, the unknown velocities v1 and v2 can be evaluated by simple substitution of v2 in terms of v1, u1 and u2, and v1 in terms of v2, u1 and u2 into the momentum conservation equation for the collision respectively. Based on these conclusive results, we can explain certain specific observations. If two bodies are of equal mass undergoing elastic collision, then using the previously derived equations, we see the exchange in velocities occur between the objects undergoing collision. To simplify the situation even further, let us assume that the target body is at rest initially. Then the simplified equations for velocities can be expressed in this way. Now, if both the objects are having equal mass, then the object hitting the stationary object will become stationary, and the stationary object should start to move with the velocity of the striking object. Now, if m1 is massive as compared to m2, then we can see the first object will move as it is, without any substantial change. However, the stationary object will now with twice the velocity of the striking object. Finally, if m2 is massive as compared to m1, then we should see there is no change in velocity for m2, that is, it will remain stationary, whereas the striking object will move in the opposite direction with nearly the same speed. This observation we often experience when we hit a ball in a wall. The ball always bounces back at nearly the same speed. Loss in speed is expected because in the macroscopic world nothing is perfectly elastic. Hence, energy is lost in every collision. Earlier, we have mentioned that we will classify elasticity with a physical parameter, that is, coefficient of restitution. It is defined as the ratio of velocity of separation to the velocity of approach. For a perfectly elastic collision, coefficient of restitution is 1. For inelastic collision, coefficient of restitution lies between 1 and 0, and for a perfectly inelastic collision, coefficient of restitution is 0. We will explain why it becomes 0 when we discuss perfectly inelastic collision in 2 dimensions. Now let us discuss inelastic collision in 1 dimension. Here, in this case, conservation of linear momentum is obeyed. However, in this case, the kinetic energy of the system will not be conserved. Kinetic energy after the collision will always be less as compared to the kinetic energy before the collision. If we obtain the coefficient of restitution for this inelastic collision, we get its value is always less than 1. But it cannot be 0 because even after the collision, the objects undergoing collisions do separate from each other. Now, let us focus on elastic collisions in 2 dimensions. If the line of motion of the 2 particles undergoing collision does not match, then we generally find collisions cannot be studied using 1 dimensions only. Here, both momentum and kinetic energy are conserved. However, there is a catch. The momentum along the horizontal direction, that is along the x-axis, and vertical direction, that is along the y-axis, is also conserved separately. Here we have to find 4 unknown parameters, but we can only obtain 3 equations. Hence, without fixing any of the unknown parameters, either by observation or by some physical consideration, we cannot evaluate the unknown parameters accurately. Finally, moving to a perfectly inelastic collision in 2 dimensions. Here, in the illustration, we have considered m1 is moving with velocity u1 and it gets hit by another object of mass m2 with velocity v2. Now, as it is an inelastic collision, therefore, after the collision, both the object must stick together and also move together. Here in this case too, the linear momentum should be conserved along both in the horizontal and vertical direction, that is along x and y axis respectively. Now in this case, the only 2 unknowns are v, that is with which speed the combined object moved after the collision, and the angle with which the combined mass deviated from the horizontal direction, that is theta 2. Here we have 2 unknowns and 2 equations to solve them. Therefore, it can be easily solved. Now, we have mentioned earlier that the coefficient of restitution for perfectly inelastic collision is 0. It is because there is no relative velocity of separation after the collision. Both the objects just stick together and move together, making the coefficient of restitution value 0. To sum up, in this chapter, we have discussed collisions, their classification, elastic and inelastic collisions in both 1 and 2 dimensions, along with the definition of coefficient of restitution to classify various types of collision.